Well, hey, good evening. Thank you for coming to the mathematics of machine learning, especially at dinner time. That means you guys are really into it, and I really appreciate that. So as to not dissuade you from eating, let's get into it. Okay, so some brief things that we're going to go through. Tell you a little bit about myself. We're going to talk about the mathematics of machine learning, which is the title of the talk. What that is going to allow us to do, it's going to allow us to see that there is in fact a way to unify the different methodologies that are out there for predictive modeling that'll lead us to the idea of actually producing explicable precision in the models we produce. And then we'll talk about some of the summary and implications from that. So first of all, who is this guy? So my background is I am a theoretical mathematician. I have a background in theoretical mathematics, in particular complex and functional analysis. And on the more applied side of things, I'm also an associate of the Casualty Actuarial Society. So anytime you get the letter in your mail that says your rates have gone up, that's me. I have 10 years experience in data science as well as R&D, predictive analytics, whatever you want to call that. And prior to that, 2 years in operations and IT. And currently my area of research is the application of theoretical mathematics to data and actuarial science. So really trying to bring together the theoretical knowledge to bear upon practical problems. And so this talk then, what's the point? I have three things that I'm going for here. One is clarity. I'm trying to make it really clear what it is we're doing when we do data science, when we do artificial intelligence, predictive modeling. Two is unification. One of the things that I think is the case, and I'll give an example of this subsequently, is that data science or predictive modeling or artificial intelligence, it seems to have this very buffet style feel to it, that there's all sorts of disparate approaches that one can take to model a particular phenomena. And I think that through the correct lens, you can see that, in fact, there is a unifying theory across all of these things. And finally, collaboration. This talk is the product of me being frustrated at the lack of literature I found on this topic. And so my hope is that by giving this kind of talk to more and more people, we can, get some like minds together and collaborate and hopefully come up with even better stuff. And then personally, my goal is to swiftly build models that are three things. One, they are precise. They actually pick up all of the signal that there is in the data. Two, that they are explicable. What does that mean? That means you can explain it to the stakeholder so that three, they can inform action. Okay, and this is a big deal because a lot of times, at least it's been my experience, when you look in the literature, when you look at different articles that are published on machine learning and artificial intelligence, and hey, we tried this approach, and hey, we tried that approach, often the focus of the article is, hey, my Gini coefficient went up, my sum of squared errors went down. And it's like, that's great. But we have to remember that when we're doing predictive modeling, this isn't a sports contest, who can score the most points, who can get the smallest, sum of squared errors. The point of the model is not the model. The point of the model is not to minimize error. The point of the model is to inform action. Now, admittedly, their ability to do this increases as their precision increases, but also as their explicability increases. And this is important, and this was pointed out more recently. This is a quote by Noah Harari, and this was at Davos in 2020. And this is part of a talk he gave where he said, look, if we're not careful with all of these computers and all this machine learning, here are some of the things that can happen. And so he says, in the not so distant future, similar algorithms might tell us where to work, whom to marry, and also decide whether to hire us for a job, whether to give us a loan, whether the central bank should raise the interest rate. And if you ask, why wasn't I given a loan? Why didn't the bank raise the rate? The answer will always be the same, because the computer says no. And since the limited human brain lacks sufficient biological knowledge, computing power, and data, humans will simply not be able to understand the computer's decisions. So even in supposedly free countries, humans are likely to lose control over their own lives and also lose the ability to understand public policy. Whew. And I thought, no. And the reason why is because, like I said, The purpose of models, the purpose of computing, it's to inform action. You're not going to get this past any regulator. You're lucky to get it past your boss if you're working in a more typical business environment. It's like, hey boss, here's what the computer says. Yeah, thanks. Why is it saying that? The computer says it. It's like, why am I paying you? And even if your boss goes along with it, there's no way a regulator goes along with it. I work in insurance, so therefore, it doesn't take too long before you get a call from, some guy in the Department of Insurance of North Dakota or Nevada going, you can't just say, well, the computer said so. So you cannot get away with that. But let's just suppose that you could. Well, even in that case, suppose you have two businesses, right? One where the business just uses the output from a computer and goes, hey, pal, that's the price. And a second business that understands what's going on and why things are working the way they're working. The second business has an advantage over the first. Okay. So now I want to briefly describe how it's been my experience that I've seen data science presented, and then talk about where we can go from there. So this is typically how I see it presented. You will have something like data science lies at the intersection of mathematics, computer science, and technology, and you get this nice Venn diagram, because if you have 4 circles, you can't make it work, but 3 circles looks beautiful on a slide. All right. And this is the way people typically think about it, and you're like, maybe you're a freshman, you're like, I think I might want to study data science. What does that look like? Looks like this, a really busy slide. And like I said, this emphasizes the sort of buffet style of presentation of data science that you'll see, say, as an undergraduate or something like that, right? It's like, how should we model this? I don't know. Pick something from the menu. How about a GLM? What is that? Well, you kind of transform your variables, take an affine combination of them, maybe put them through a link function. Cool. How do I get my parameters? Well, the error comes from some sort of distributional assumption. Cool. How about a tree? A tree, what's that? Well, it's just really, the sum of products of indicator functions. And the error associated with that, distributional assumption? No. Gini impurity, information gain, variance reduction. Well, where do the parameters come from? You guess and check. That's what goes on inside of a tree algorithm. And then, of course, a random forest is just an extension of that idea. And you'll observe that I use the same functional form for both, because if you do the work, you can actually find out. And this is in one of the appendices of the presentation. That you can write a random forest as a tree. How about Mars? Multivariate adaptive regression splines. Error, sum of squared errors, great. And how about single layer perceptron? That's really cool. Neural nets, we hear about them all the time. Wow, that sounds awesome. What's the minimization routine? Back propagation. So you have these things that seem to be fairly correlated when you study them, right? There's the functional form, the actual form of the output, and then there is the error associated with trying to figure out the parameters of the model, and then there's the minimization routine, and these things seem to be, compressed together. And you go, why is that the case? Is it the case that one of these things determines the other? I don't know, that's kind of odd. And then finally, you get ensemble models. And I love these things. You use multiple learning algorithms to obtain better predictive performance than could be obtained from any constituent learning algorithms alone. So what that really means is that we don't know, right? We're just taking stuff and averaging it together. And from a practical standpoint, you get that, right? You say, what are next year's projections? 3 of your employees come in, one guy says $1 million, another guy says $3 million, third guy says $2 million. And immediately you go, $2 million. So I get that from a practical perspective. But from the perspective of actually pushing the discipline forward, that's really kind of falling on your sword. Okay. And it turns out that it's really not clear to many people how to proceed in any sort of canonical or algorithmic way. And so the elements of data science, that's one of the courses you can take at Amazon. Just log in, they got like a ton of different courses you could take. Elements of data science, data processing and engineering, so these are the different sections in the education. How to handle missing values, I love it. Drop columns or rows. We got one missing value. Maybe we should just get rid of the whole thing. Oh, we got a missing value, throw the record out. Yeah, why am I paying you? Okay, or impute the mean, medium, and mode. Again, I'm not saying there's anything wrong with these things, but what is the driving philosophy there? What is the underlying thought that gives rise to these recommendations? Feature engineering, here's what they have to say about that. It's more of an art than a science. That's kind of a bummer in data science. What do they say? Use some rules of thumb. How about your intuition? It's like, well, that's why I'm here. How about a square, some nonlinear transformation? I love the phrase nonlinear transformation because it's true that in life you have linear transformations, you have nonlinear transformations. But that's really big. There's a book once called, what is it? Ordinary Linear and Nonlinear Differential Equations. It's like, yep, that's pretty much it. Try not to overthink. Thanks, pal. Some feature engineering transformations. How about some polynomial? And then how about some non-polynomial? How about a log? How about a sigmoid? Now, am I being a jerk? Am I just, and how do you decide among these things? Am I being a jerk? I come here, Amazon puts on this lovely thing. Am I biting the hand that feeds? No, I'm not. Because here's the thing. The problem is actually deeper than some training that's offered. So this is a quote from the original text on decision trees, classification trees. So this comes from Bryman. This is like 1984 or something like that. And so this is one of the originators of this talking. Goes, binary trees give an interesting and often illuminating way of looking at data in classification or regression problems. They should not be used to the exclusion of other methods. We do not claim they are always better. It's just another tool. So this is the originator saying this. He doesn't even know. McCullough and Nelder, so these are the guys that had the main paper on generalized linear models. So generalized linear models, you might say, what if I need a nonlinear transformation? They say, great, we're going to devote chapter 9 of our book to that. But even in chapter 9, really the discussion centers around if you wish to include some transformation and you know the parameter on which the transformation lies, well, then you can augment your code in a certain way. So they don't really tell you how you might apply a nonlinear transformation to your data. And finally, for the Mars technique, so this is Friedman writing in 1991, and the original paper on the Mars technique, it's like 70 pages. It's really long for a journal article. Most journal articles are about 10, 15 pages, if you don't count the tables and whatnot. He doesn't even address it. It's just, here's something I tried. Here is something I tried. Here are the results. Maybe it'll work for you. Okay, so disappointment all around. I'm just here to complain. No, here to solve problems. All right, so here's a reasonable question. Do functional forms, that is to say the form of your prediction, error measurements, and minimization routines, do those have to be packaged together? That's a reasonable question. Is there a canonical way to select a functional form? Like, is there some way to, of all of the different things that you can do, is there some way to sift through that in a reasonable fashion and select a functional form? Is there a canonical way to select a measurement of error? And the answer to that one briefly is yes. Sum squared errors always works, and the brief answer for why is because, well, we'll see later, there's something called the conditional expectation, and that can be seen as a projection onto a set of random variables, the Hilbert space projection. And finally, is there a canonical way to select a minimization routine? And the answer is, And the reason for that is if you've ever taken a course in numerical analysis, what you basically find is, here's a minimization routine, and you know all these things if you played with, like, say, the different optimization packages in Python and R and whatnot, is that, or even really in SAS, right? Because you can select the routine that you want to use, and there's like 8 of them, or something like that. And so if you take a course in numerical analysis, what you can do is, in the textbook, it says, here's a routine, here's an example where it works, here's the math, why it would work, here's an example where it fails, look, one of these assumptions doesn't work. Okay, so what we're going to focus on is there a canonical way to select a functional form and its related features? And so this needs then a little bit of a reimagining of data science. So this is how I actually see data science. I do not see data science as a Venn diagram. I see it as a pyramid with the mathematics at the bottom. And why is that? Is it because I'm a mathematician, so I got a dog in the fight and I'm like really proud? And the answer is no. It's because mathematics indicates what to compute. It's the thing that you have to do first before you even grab a keyboard. Computer science, on the other hand, determines the implementation of the computation. So for instance, suppose that you want a routine that solves a system of linear equations. There are multiple ways you can do this, right? If you've taken a course in linear algebra, you know that you can reduce things to reduced row echelon form, solve it that way. You can compute the inverse of your matrix, solve it that way. You can use Cramer's rule, God help you, solve it that way. And one of the many useful things that has come out of computer science is that people have gone through and they've actually said, okay, if I take this approach, what's the runtime for that algorithm? And they basically said, do reduced row echelon form, forget Cramer, although Cramer is very useful for theoretical considerations. And finally, technology, that's the tool that you use to perform the computation. So you use Python, you use R, you use SAS, whatever. Okay, but I want to focus on this idea of that mathematics indicates what to compute. So here's a question. Why compute that? So that's one of the first things you learn, right? That's what even Stats 101 students learn this. People who hate math, who have to take stats because they need a math credit, they just grind their teeth. They still learn the sample mean. Why do we bother with this? When we could bother with that. Why, instead of taking the sample mean, don't we take the product of our data, to compute the cosine of it, exponentiate it, and add 54 to it? Why do we do one and not the other? Well, here's my claim, is that, and this goes back to the idea that mathematics tells you what to compute. Something that doesn't seem to be obvious, perhaps, is that given a set of data, there's an infinite number of things you can do with it, right? There's an infinite number of numbers. There's an infinite number of ways of putting those things together. I just pulled the second one out from the ether, as an example. There's an infinite number of things you can do. How do you decide among them? How do you take the field of infinite potential and reduce it down to a set of finite steps? And the answer is, well, that's what math gives you. The reason you compute the sample mean is because the sample mean has a well-developed theory underlying it. We know what the sample mean does. We understand its properties. We know that with the strong law of large numbers, that as n goes to infinity, the sample mean converges almost everywhere to the mean of the population. We know that under certain conditions, the distribution of the sample mean is asymptotically normal. The central limit theorem gives us that. That's great. We know what this thing's doing. It does what we want it to do. The second calculation, there is no theory underlying that calculation, as far as I know. See me afterwards if you know, though. Okay. And so then a reasonable question is there some mathematical theory that addresses predictive modeling? And my claim is yes. So here we go. Now, the typical way that you frame modeling problems is people often desire to estimate quantities of interest using known information, right? And so one way that you might phrase this is you would say, what would you predict using given information? And in fact, that is the way that you see it programmed, right? When you're using Python, when you're using R, for instance, there are functions that say predict. That's how they're thinking about it. What would you predict using this? And even in SAS, the syntax for the different procedures is something like P underscore, and then you can name the thing that you are predicting. That's what the P is there. But another way that you could say it is, what would you expect using given information? Okay, well, fortunately for us, and this is one of the great things about math, math formalizes our language and our intuition. And so the mathematical formulation of what would you expect given certain information, that is an actual statistical object. It's called the conditional expectation, and it's denoted that way. And now you say to yourself, hey, pal, that's great. I'm glad you can write something down on paper. How does that help us? That you've just, assigned some notation to it. Fair question. Okay, so the real question is, how do we determine this thing? So right now, it's this abstract statistical object. How do we determine it? Who knows? All right, well, here's the thing. By definition, we know that this is a random variable. It's a measurable random variable, and it's measurable in the space generated by the predictor variables. Okay. And moreover, we know, and this is a result in Billingsley, that there is a Borel measurable function on Rn into the real line that equals this statistical object. Okay, great. So now we've gotten somewhere. We know that our conditional expectation is a real valued function defined on Rn, and it's Borel measurable. And you say, why do we care about that? And that's also a fair question. And the answer is, and it comes to us from a guy named Lucen with an S as opposed to Luzen with a Z, but it's spelled both ways if you look at the literature, so keep that in mind. This version of the theorem is the most powerful version of the theorem of which I'm aware, and this can be found in Rudin's real and complex analysis. Rudin always going for the most general version of a theorem that he can. So what does Lucen's theorem tell us? It says, well, it turns out that if you hand me a measurable function, which again is a kind of an abstract concept, if you hand me a measurable function, it's an abstract concept, I can hand you back a continuous function that equals the measurable function. And you're like, that's a step in the right direction, because measurable, you got to take like typically a graduate course in measure theory to know what a measurable function is. But continuous, oh, sweet. Now we're at pre-calc levels, right? Because you learn what a continuous function is in pre-calc, right? It's a function that you can write without picking up your pencil or your pen. Okay, so I hand you a measurable function. Lucen hands me back a continuous function that equals it, except on an itty-bitty little set of the real line, of the plane. So they are equal except on a set of very small probability. So with probability close to 1, this continuous function equals this measurable function. Okay, but wait, there's more. Call now. It turns out that this continuous function has what's called compact support. Okay, so what does that mean? Compact support, when you're talking about a compact set, that has a more general topological meaning, but in Rn, which is where we are, because remember, this function is defined on Rn. If you're in Rn, a compact set is just, it just means that you can put it in a box. That's what it means. It means that it is, you can put it in this box. It is closed and bounded. Okay, and support, what does that mean? Well, it means that it's 0 outside of that region. And so we had this previously sort of abstract idea. We had this measurable function. It's defined on Rn. You could say that's too abstract. Let's replace it with this continuous function. And in fact, it's not just it's not this necessarily extraordinarily complicated thing, because outside of some box, it's 0, and that's really easy to understand. Okay, and so you might have a situation that looks like this. So the purple there is supposed to represent the continuous function where it is non-zero, and outside of that region, it's 0, and then we put that whole thing in a box. Okay, so now what I claim, and you're just going to have to go with me on this for a moment, what I claim is that it would be much more useful if we could put this region inside of the unit square. And you say, why would we do that? And it's like, fair question, just trust me here for a moment. Okay, and how are we going to do that? Well, here's one way we do it. We do it the exact same way that you do all of your data analysis problems, right? One of the first things that people typically do is they standardize their variables, right? You know, subtract the mean, divide by the standard deviation, or whatever technique that you like to do in order to put all of your variables sort of on the same scale, right? We'll just do the same thing. We'll scale it, and we'll move it. And now we have taken the support of the function. Again, this is where the function is non-zero, and we've put it inside of the unit square, and then just for the fun of it, I mean, it's 0 outside of the purple, but we can just pretend that, you know, it's just a continuous function on the unit square. Okay, so now we're in good shape. You might say, really? I say yes, and here's why. because we started off with this very abstract statistical object known as the conditional expectation. From that, we were able to get a measurable function. From the measurable function, we got a continuous function. From the continuous function, we were able to put it into the unit square, and this thing equals our original function with near probability 1, although not completely. Okay. So what does this tell us? It tells us that the conditional expectation is a continuous function on the unit hypercube for all intents and purposes. And this is the big deal. This is the big deal. This is the unification of methodology, is that whatever you are trying to do, remember that you might as well assume that whatever it is you're trying to predict, whatever it is you're trying to model, it's a continuous function on the hypercube. And you say, why does that help? Well, a few things. One, it's continuous. We know what those things are. Two, the hypercube is a very specific set, right, in Rn. It's not just some crazy looking region. You know, the hypercube, you know, it's the unit interval, it's the unit square, it's the unit cube, and on into higher dimensions. It's a very specific set, but more importantly, it's well studied. We know what kinds of things can be used to approximate continuous functions on the hypercube. It's a very well studied area. So for instance, we know that indicator functions, things that turn on, turn off, those kinds of functions, very simple functions, on and off, those can be used to those can be used to approximate continuous functions on the hypercube to any degree of accuracy that we want. Okay, and so that, for instance, comes from that comes from the fact that continuous functions are uniformly continuous on a compact subset. So indicator functions can approximate any continuous function and therefore can work all the time when you're doing your predictive modeling. Multivariate polynomials coming to us courtesy of the Stone-Weierstrass theorem. So Weierstrass proves this result originally in the 1800s, and then Stone greatly generalizes the result in the early 1900s. So multivariate polynomials always work. They always approximate continuous functions on the hypercube, and therefore always work in your modeling exercises. Neural networks, everyone's favorite function around here, or form of the mean around here. Neural networks always work. Why? That comes from Cybenko's work of 1989, I believe. Trigonometric polynomials. Let's not leave out the electrical engineers and anyone doing signals work. Multivariate trigonometric polynomials always work. They approximate continuous functions on the hypercube to any degree of precision that you like. They always work. And in a univariate sense, I believe it's multivariate, but I haven't proven it yet. Piecewise linear functions always work. They pick up all the signal. They can approximate any continuous function on the unit interval. And this comes again from the fact that continuous functions are uniformly continuous on compact sets. So, and then this is just another fun observation. Observe trees, polynomials, piecewise linear functions, trigonometric polynomials. What are they? They are linear combinations of functions of the predictors. Why is that important? One, again, in mathematics, this is a field that is well studied. What sets of functions, when you consider all linear combinations of them, often called their span, can approximate everything. That's a well-studied idea in mathematics. But more importantly, for us and for our work, the important thing to notice there is that, well, that's what almost all of our modeling software does, right? It's like, put a bunch of transformations of your input variables in, and we'll give you a linear combination of that. It's like, well, that's useful, thank you. All right, so here's an example. So I tried to think up a function that I thought would give a Calc 1 student a heart attack if you asked them to differentiate it on an exam. And so this is a crazy looking thing, you know, you got trig functions, the exponential function, there's a log in there just because I'm a jerk. Okay, so suppose that is the actual random variable. Now, of course, in real life, you never know this. You know, the actual conditional expectation, that's just known by God. Instead, what you get is the data. And so what we have here is we have the actual function, that's the white line, and then the The green is the data that I generated. And here's the thing. If you start thinking in terms of sets of functions which can approximate continuous functions on the hypercube, then you could start examining those things, and here's what you get. So, can we see that? Okay, yeah, so the blue is the model here. So using indicator functions or step functions, the data just tells you where to put the jumps, and it tells you the magnitude of the jump. Because you're using a very particular type of function, which is easily parameterized, you can say, what happens if I use 1? What happens if I use 2? What happens if I use 3? What happens if I use 4? And the data itself will say, well, then you need to put that there, you need to put that there, the magnitude's got to be this. Again, use a polynomial function. Picks it right up. And again, the data is what tells you this. You don't have to think too hard about it. You just say, linear term, quadratic term, 8th power, 9th power, whatever it takes, you know. Just whenever I run out of statistical significance, that's what I'm using. Okay, piecewise linear model. It looks like there's about 5 terms in there. Piecewise linear, why do I love it? Connect the dots, not that difficult to understand. Picks up all the signal. Again, the data tells you where to change the slope and by what amount by trying more and more and more and more terms. Okay, this one goes off the rails a little bit at the end, but that's all right. So it's still got a 0.97 correlation, so I don't want to hear any bellyaching. But this is using trigonometric polynomials here. And again, how many do you use? You try 1, you try 2, try 3, try 4, try 5. At some point, you run out of statistical significance. Okay, so this leads to the idea of explicable precision. And so the idea of explicable precision, this is what I've titled producing a model which picks up all of the signal that you can from your input variables, and you can explain it to a stakeholder. That's why it's explicable. And so, here's the step. Think in terms of functions that can approximate continuous functions on the hypercube, preferably sets of functions that have a dense linear span, because then you can make ready use of all of the linear predictor methods that are already packaged. Okay, and so what's the path to victory here? Well, there's a few things here. 1, choose a functional form that's intuitive. 2, choose an error that allows you to make statements about convergence. 3, choose a selection scheme that achieves the convergence you want. 4, choose a selection scheme that tends to parsimony. And 5, prove theorems to make sure you are right. So let's go through these. So choose a functional form that is intuitive. What do I mean by that? Well, here's the thing. Model opacity, you know, people talk about a black box, although it's not clear to me that a white box is any better. I think what you really want is a clear box. But anyway, so when you're talking about model opacity, understand that model opacity is defined in terms of the stakeholder, right? It's whatever the stakeholder understands. And so it's not the case that you can prove a theorem that says this kind of model, everyone always understands it. You know, for us, a neural net, it's like, no problem. I get what's going on in there, you know. But for my mom, linear regression is just too much, you know. So model opacity is defined in terms of the stakeholder. So that's outside of your control. But here's what's in your control, is that you can choose models which are relatively easy to understand, and so that's why I go back to the step model here. Because what's this thing doing? And obviously this could be generalized to more dimensions, but what's this thing doing here? What it's doing is, when you're applying a step model to things, it's grouping, right? Wherever the graph is flat, it is grouping together those x values, right? And treating them all as though they're the same. So that's the explanation of using a stepwise function. The stepwise function groups together the values of the input variables. And so it also answers a question that often comes up when you're in business, because, you know, people love to group numbers together. Like for instance, like with COVID, you know, it was like, well, look at how COVID changes when you consider the different age groups. And the question is always, where do those age groups come from? Why'd you put those ages together, not those ages together? And the answer is, well, you can use an approach like this, and it will just tell you what ages you should put together. And again, I also like piecewise linear functions because, like I said earlier, it is simply Connecting dots, all you're saying is that, your rate of growth is this much here and that much there. I used this just the other day to parse out the inflation rate for a particular line of business at work. And so here's the deal, is that, the more sets of functions that you have to work with, and this is why I say proof theorems, demonstrating that certain sets of functions can approximate continuous functions, the more sets of functions you have, the more sets of functions you have to work with, and that might be explicable to the stakeholders, right? So like maybe it's the case that the first model you create, you show it to someone, they go, man, I don't know. But maybe if you use a different set of functions, you'll create a model and they go, oh yeah, okay, got it, So proof theorems that show that different sets of functions can approximate continuous functions on the hypercube. The more sets from which to choose, the better. Okay, choose an error that allows one to make statements about convergence. So this goes back to what I was saying at the beginning. Why is it do we package together ideas about the functional form of our model and the error which goes along with it? It's not clear to me at all. So here's what we do. First, observe. There are multiple ways to conceive of closeness and convergence. One of these ideas is called convergence in distribution. And you say, what is that? And the answer is, you already know. It's a central limit theorem. When you say that the distribution of the sample mean converges asymptotically to a normal distribution, that kind of convergence is called convergence in distribution. So you're already aware of it. Here's another one. LP convergence. When p is equal to 2, this is your typical Euclidean distance in the plane, for instance. Convergence in probability. I'll give an example of that in just a moment. Almost sure convergence. What is this? Again, you already know this. This is the strong law of large numbers. This is what is invoked when you say, oh, by the way, my sample mean converges to the mean of the population. Converges how? Almost surely. And stop calling me Shirley. So what I had said earlier, that if you have a set of functions that can approximate continuous functions on the hypercube, and I hand you a conditional expectation, what you can do is you can find a sequence of functions in that set, and affine transformations. What's an affine transformation? That's simply a scalar and then a movement, and so whenever you standardize your data, whenever you subtract the mean and divide by the standard deviation, that's an affine transformation. And so basically the affine transformation is what took the purple region, right, and put it into unit square. And so what we were saying earlier is that we can approximate things and they will be equal except on a very small area of probability. They will be equal except with probability 0.999 or something like that. So that's convergence in probability. Okay. And here's the thing. Whatever goodness of fit you choose, whether it be sum of squared errors, whether it be Gini, whatever, just make sure that it coheres with some sort of convergence. Convergence of distribution, LP convergence, convergence probability, almost sure convergence. Okay, so what next? Choose a selection scheme that achieves the convergence you want. So here's an example of such a scheme. Typically, they involve looking at increasingly complicated sets of functions. So if you think about trees, there was one article, and they said, don't be afraid to go 15 layers deep in a tree. And I thought, how am I going to explain that to the Department of Insurance? So instead of going 15 layers deep immediately, what you can do is you can say, well, what if we go 1 layer deep? See how far we get with that. How about 2? How about 3? And so on. Increasingly complicated sets of functions. Mars, do main effects, then do second-order interactions, then do third-order interactions. Perceptrons, they don't necessarily have to be single layer, but people often talk about the architecture of a neural network, right? Well, you can rank order in terms of complexity the architectures of neural networks, right? Because you could say, okay, well, how many layers? That's a positive integer. How many layers? How many nodes in each layer? And what you can do is that gives you a grid, right? That gives you a grid of integers, and then what you can do is you can order that grid of integers in a way that allows you to build your neural network up, from simple to complex. So whatever it is you're doing, and here's the general scheme, given a set of functions that you know can approximate continuous functions on the hypercube, what you can do is you can write it as a union of increasingly large sets of functions. And the idea then is that you construct each of those sets of functions to be increasingly complicated, however that's defined. Again, main effects, second order interactions, third order interactions, more and more and more nodes and layers in your neural network, that kind of thing. Then you can select a method to select the best candidate from that set of functions. And so what would that be? That's precisely what you're doing when you are, say, running a GLM or something like that, right? In the simplest illustration, when you're putting a line through data, right? How do we select from among the infinity of lines? And the answer is, well, you minimize sum of squared errors. So you need to state that. You need to state a method to select the best candidate. And again, whatever your scheme is, make sure when you combine it that it coheres with your goodness of fit, so that your scheme and your goodness of fit work with your idea of convergence. Okay, choose a selection scheme that tends to parsimony. What do I mean by that? Well, model opacity is an intuitive thing, right? Model opacity is defined in terms of the stakeholder. But parsimony is, you can actually give a mathematical definition to that. It's not very sophisticated. It's simply how many parameters are in your model. The more parameters that are in your model is essentially you making more statements about what is true, right? And so the fewer parameters in your model, conversely, is you making fewer statements about what is true. And so parsimonious models are the statistical equivalent of epistemic humility, that you're not saying anything more than you have to say. Okay, so the path to victory. 1, choose a functional form that is intuitive from the sets of functional forms that we know can approximate continuous functions on the hypercube. 2, choose an error that allows one to make statements about convergence. 3, choose a selection scheme that achieves the convergence you want. 4, select a scheme that tends to parsimony so that you're not saying anything more than you need to say. And 5, prove theorems to make sure that you are right. Now, why do I emphasize this? Is this because I'm a curmudgeonly mathematician? I am, but that's not why I emphasize it. It's because when you read, at least when I have read a fair amount of the literature, when I've read a fair amount of articles, a lot of the articles that I've read kind of have this feeling of, hey, I had this project, I used this technique, here are the results. They were better than what I was using before. Maybe it'll work for you. And I understand the importance of empiricism, even in mathematics and computer science. Nonetheless, you can't of necessity generalize from those articles, right? You don't know if what they're saying will work in all situations. You don't know how much you can extend what they're saying. And that's the importance of actually proving theorems, so that you know that it always works in all cases. So summary and implications. Consider separately the functional form of the conditional expectation, the measurement of error, the minimization routine. Once you have a functional form and you have a concept of error, then what you can do is you can, then you can actually do the math ahead of time to help out the minimization routines, right? So this is an experiment that I've performed now a few times, and by I mean my poor interns who I yell at and make them do things. And what you can do is, if you just hand a function to a minimization routine, it will give you back, say, the right answer about where it achieves its minimum. But what's it doing internally? Well, most minimization routines, they make use of gradient methods, right? They make use of the derivatives. And so if you just handed a function, what the minimization routine is doing, it's saying, hey, thanks a lot, pal. I'll be off to the side here. numerically, I'm just going to crank out a numerical approximation to the derivative. If you hand it the derivative, it's been my experience that you reduce your runtime by 2/3 to 3/4, and that's savings, man. We took a process that initially took 9 hours down to an hour and a half doing things like that. Okay, and again, use functional forms that can approximate any function that's continuous on the hypercube, and went through the rest of that stuff. And so I will end with saying the main point, which is remember what we're doing. We're not building models for model's sake. We're not building models because we're trying to brag about our error. What we are trying to do is we are trying to inform action. That's the goal. How do we do it? Through precision and explicability. The precision comes from considering functions which can approximate continuous functions on the hypercube, and the explicability comes by looking at ever more sets of them so that we can show things to our stakeholders that they understand. So that's that. Thanks for coming. Are there any questions? Yo.
So when we're doing from measurable to continuous, we're losing a little bit. So our approximation
Yes.
is going down.
Correct.
Moving from the continuous into the unit squared into the hypercube.
Hypercube.
What do we lose there?
Nothing.
Okay.
Yeah, so you lose in two places. Once is, you lose in two places. Once is when you swap out your measurable function for your continuous function. That's where you lose. Those things are equal to each other with probability 0.9999, something like that, but not repeating because then it'd be 1. So you lose there, but then you also lose when you approximate the continuous function with a known set of functions. Because again, the continuous function itself is it's an abstract object. Again, it's not as abstract as the conditional expectation, but it's still abstract. And so what you get then is you get a model which is really close within error, within tolerance, say, of the phenomenon you're modeling with probability 0.999, something like that. And so you lose in two places. Any other questions? Oh, yes, sir.
Continuous function that comes up from the data seems to be dependent on the initial set of data that you have. In machine learning, typically, as you run the model and you learn new stuff, you get a bunch of new data gets added to it. How do you ensure that the new data is within the space of the existing data that you already have? And if it doesn't mean that your continuous function needs to be continuously updated?
Yeah, okay, so two good questions. So the first is, as you're getting more data in, how does that impact the construction of your approximation? And therefore, does that approximation need to be updated? Did I get that roughly correct? Yeah. Okay. So the answer is, the answer is an answer I love to give to my boss, or really any stakeholder when they say, well, will this work in the future? And my answer is, I don't know. The future's unknowable. Why are you asking me? I'm not a crystal ball. You're doing the best you can with what you got. So the answer is, yeah, if you have some data set, right, and then just like new data comes in, it's entirely possible that you're going to have to recalibrate. Absolutely. Because it's new information, right? And so, nonetheless, you could still make use of these techniques. It's just that what you would have to do is, it'd have to be some sort of like Lambda job or something like that. It's like new data hits S3 bucket. Okay, resolve for where you put your jumps if you're using a stepwise function, or resolve for the powers of the polynomial that you need, resolve for for the coefficients on those things. Yeah, that's entirely possible. Yes.
If I'm using this in the real world, then my strategy should be figure out a continuous function, approximate it, run the model. If the data is good, I'm happy. If the data is bad, then
Well, it's not so much that the data is going to be bad, though. The data is the data. The question is whether or not your model is worthwhile.
I guess my question is, if it's working, then is it better to not update the business function so that I just change them all completely?
Fair question. So the question is, basically what you're asking me is, how do I know if my model, as it exists today, is good enough, even with new data? Is that roughly correct? Yeah. Okay. I'm going to give another evasive answer and say it depends. And the reason why I say it depends is because it depends on what you're using the model for. So like I said, what we're trying to do here is we're trying to inform action. And so maybe a minor error, the result of a minor error is like, oh, we mispriced a policy by 3 cents. Darn, that you can't tell when you have a target variable that has a high variance, right? It's like you can't tell anyway. But maybe if your error is off by too much, maybe now the sensor fails. Maybe now the plane goes down or something like that. And so that's why my answer is evasive, because it depends on the effect of the error, which is typically a function of the magnitude of the error. And so that's a meta data science question, really. Does that make sense?
Yeah.
Cool, thanks. Yeah. Any other questions? Sorry, the lights are really bright up here. What's up?
Thank you very much for your talk.
Yeah.
You motivate your approach mainly saying, I want something that's explainable to the stakeholders.
Yes.
So if they don't mind, do you think there are other advantages, for instance, in computational networks, using more explainable methods?
Are there computational benefits to using more explicable methods? I have no idea. I'm sorry, I don't know. It is a curious thing to me, though. I'll answer your question with an anecdote. I'm sorry, I don't have anything better than that, but perhaps it'd be illustrative. So one time, so I told you earlier that the point of models is it's not a competition. So now I'm going to tell you a story about when I did a modeling competition. So my friend and I, we both worked at Farmers. We had to predict something, and for the fun of it, we just decided to both go at it and see what happened. And so he took like the approach of random forests, with millions of trees and neural networks and all this stuff. And I have to admit, he did beat me. His Gini was 0.77, mine was 0.76. Went home, cried in my beer, fine. But the thing is that his model had 10,000 parameters and mine had 151. So now, those parameters that were in my model, yeah, it took me a minute to figure out where to put them, So that took some effort, whereas the neural network, just computed it, but it was computing a lot more stuff, so I don't know. This is very rambling, I'm so sorry. I wasn't prepared for that question. But now that I'm thinking about it, as I'm verbally processing in front of a live audience, it does occur to me, here's the real benefit of, say, using something like a neural net, is that you don't really have to think about your transformations. Almost everything that I've been talking about up here is, here's a set of transformations at work, you have to think about them. There are algorithmic ways to think about them. In fact, I've got an intern deriving them right now. Actually, not right now, he's in Italy right now, but when he comes back, he'll be back to the grindstone. You do have to think about what you're doing here, and that requires extra effort, which requires extra programming, but then the benefit is on the back end, where you get things that you can understand what they're saying. That's why I was able to tease out inflation rates in a particular line of business while controlling for the fact that, well, in this state, the statutes are this, and in this state, the statutes are that, and so I was able to control for all those effects and tease out the inflation rate using techniques like this. Whereas if you just put, what were the variables in there? Time, he told me to just do it in an afternoon. Time, state, the kind of hospital it was, a medical malpractice, by the way. you know, if you put that in a neural network and then said, okay, what's the inflation rate? It's like, I don't know. I can tell you the weights on the time variable, but I don't know. And so I think using these techniques is very much dependent on what it is you're trying to do. And so again, what we're trying to do here is we're trying to inform action. In some cases, all you need is the prediction, right? And in those cases, it's fine. Use whatever kind of black box you want. But in cases where a human needs to look at it and say, what is this telling me? You know, that's the use of these techniques. And these techniques typically do require you to think more about what you're doing. I'm like I said, I'm in the process of trying to algorithmatize those things, but those packages are not out on Git yet. So that was a rambling answer. Does that help?
Yeah. So that, I may add one point. I think if you scale the model, or if you follow them on scale, the advantage is often that you use significantly less effort if you, for instance, use the linear regression versus the complicated neural network. And I think the value is not necessarily explainability, but can often be computational cost.
I hope so. That'd be great. It'd be great if I got them both. Any more questions? All right. Hey guys, thanks for skipping dinner to come to this. I appreciate it.